I've been trying to build a better understanding of how PPO actually works. So, in order to do that, I built a simple obstacle avoidance environment. I wrote my own PPO implementation. I trained an agent on it, and then I compared all of that against the same environment in PufferLib. What you're seeing here is one of the agents I trained playing that simple environment. The goal for me was just to build an intuitive understanding of what's actually happening under the hood. And in order to do that, I had to start here. This is the Generalized Advantage Estimation paper by John Schulman. Honestly, if I was doing it all again, I would not start here. This paper is super math heavy, and I pretty much had to brute force it to understand everything. But this paper is really important because it helps explain how we address the credit assignment problem, which is the long time delay between actions and their positive or negative effect on the rewards. The best way to think about this is to think of two different agents. One where we have rewards along the way, kind of like breadcrumbs, leading it towards the behavior that we want. And the other one where we only reward the desired behavior. In reality, what we want is more like the agent on the right, because the agent has more freedom to discover its own solution. And the hard part is figuring out which of our early actions deserve credit for that final reward. The beginning of this paper is basically a review of the fundamentals, policy gradients. Policy gradients are how we actually update the weights of the neural network as we train with our environment. Now, looking at this equation right off the bat, it looks pretty intense. But if we break it down piece by piece, it's really not that complicated. G is just the gradients that we return. It is what we use to actually update the policy. Pi sub theta is the actual policy. So when we say updating the policy is actually just the neural network itself. The theta here means it's the neural network for the agent. What you'll see as we explain this is we also have a critic. We'll get to that later. So when we combine this stuff in the parentheses, A sub t given S sub t with our policy, all this means is the probability that our policy, given a specific state, S sub t, is going to produce a specific action, A sub t. And in this equation, that whole section, log of pi sub theta A sub t given S sub t, is just us taking the log of the probability that for each state it's going to produce a given action. This upside down triangle is called nabla. All this means is that we're taking the gradient with respect to our policy, theta, and we're back propagating through the computational graph. Now, working our way left, psi sub t is just a placeholder, so the GAE paper here can show us all the different methods that have been used over the years. This is the credit assignment part of the equation. It decides how strongly we push the policy towards or away from the action it took. The GAE paper shows a few different methods that we can plug in here. The simplest one is the first one, which is just the raw rewards themselves. A slightly smarter version is the TD residual, where we compare what actually happened to what our value function expected would happen. And then the one we actually care about, the one we're going to talk about later, is the advantage function. The advantage tells us whether this action was better or worse than expected for that state. All the way on the left, this E is called the expectation. It is a statistics term that means the empirical average over a batch of samples. For our case, it's the average over all the samples in a given rollout. Now, like we said, what we care about in this paper is the advantage function. So this is the equation that we're actually going to be using. This is the equation for the advantage function. Here, V of S sub t is the value of the state. It means if we look at just this state, how much future reward do we expect to get on average if we keep following on our current path? Q of S sub t, A sub t is similar, but now we include the action. It means from this state, if we take this action, how much future reward do we expect to get? So the advantage is just the difference between those two. It tells us whether this action that the policy decided to take was better or worse than the average action we expected given that specific state. Positive advantage means the action did better than expected, so we want to increase the probability. Negative advantage means it did worse than expected, so we want to decrease its probability. But the catch is that we don't actually know the values for Q, V, and the true advantage. These are just theoretical quantities. If we already knew what was going to happen after taking each action, then we wouldn't need to learn by interacting with the environment in the first place. We could just pick the best action. But reinforcement learning is hard because we don't actually know those values. The agent has to try actions, then we collect those rewards, and we use that experience to estimate which actions were better or worse than expected. Because of that, we have to find a way to estimate them. That is where the critic comes in. The critic is just another neural network that tries to predict V, how much future reward we expect from this given state. This is where delta comes in. Delta is the critic's one-step prediction error. Before the action, the critic predicted that this next state was worth V of S sub t. Then the agent took another action, received a reward, and moved into the next state. The critic estimates that this next state is worth V of S sub t plus 1. So delta compares two things: what the critic thought this state was worth before the action, and what the state looks like after one step of actual experience. So delta is the reward now, plus the discounted value of the next state, minus the critic's original estimate of this state. If delta is positive, the action led to a better result than the critic expected. If delta is negative, it led to a worse result than the critic expected. Now that we know what delta is, equations 11 through 14 make a lot more sense. Equation 11 is just the one-step version. We look at one delta term. Equation 12 looks 2 steps ahead. Equation 13 looks 3 steps ahead. And equation 14 generalizes to k steps. So the basic idea is delta is asking us if things turn out better or worse than expected. We're just asking that question over longer and longer windows of future experience. Going back to our equation for delta, we skipped over a new symbol here, gamma. Gamma controls how much future information counts. A delta right now matters the most, and then a delta one step from now matters a little bit less, and then a delta 10 or 50 steps from now matters even less. Equations 11 through 14 showed us different ways to estimate advantage by looking different distances into the future. But GAE in equation 16 here blends them all together. The final estimate is a weighted sum of future delta values. Delta now plus a smaller amount of delta one step from now, plus an even smaller amount of 2 steps from now, and so on. This is where lambda comes in. Lambda controls how much the longer future we include. Low lambda makes the future fade out quickly. High lambda lets future experience matter for longer. So gamma and lambda together control how far credit or blame reaches backward through time. Now, we haven't even gotten the PPO yet, but the GAE paper we just went through lays all the groundwork. So explaining what PPO is and how it works is actually going to be really easy. Up to this point, we've built the core idea behind policy gradients. The policy gradient gives us a direction to update the policy, and GAE gives us a cleaner advantage estimate, which tells us how much credit or blame we assign to each of the actions that we took. But policy gradients and GAE alone don't answer the next question, which is how large of an update should we make to the policy? If the update is too small, then learning is slow. But if the update is too large, then the policy can change too much and it can collapse. PPO is what solves that problem. Before PPO, John Schulman, who created GAE and PPO, had another method called TRPO, Trust Region Policy Optimization. TRPO worked by putting a hard constraint on how much the policy was allowed to change in one update. That made training more stable, but it also made the update step really complicated and expensive. PPO was a simpler version. It keeps the same basic idea. Don't let the policy make a giant step, but it does that in a way that's very easy to implement, as we'll see. The core trick is the clipping mechanism, which is shown in equation 7 here. The important part here is this ratio, R sub t of theta. This compares the new policy after we've done an update. So you can think about this like we're going through our epochs and we're back propagating and we're updating our weights, and then we're comparing how that new policy performs with the new weights to the old policy before we did any back propagation. The second important part is the clipping mechanism here. Most of the time, epsilon is going to be 0.2. So you can see for this example, all we're trying to do is we're keeping that ratio between 0.8 and 1.2. Now you can see here that what we're doing in this equation is we're multiplying the advantage by the ratio. So again, the advantage tells us whether or not we wanted that action to become more likely or less likely. Positive advantage means we want to reinforce it. Negative advantage means we want to move away from it. The minimum here is really important because it ensures that we always choose the more conservative policy. It's a little bit counterintuitive, so let's look at an example for two situations. One where our advantage is positive, and the other where our advantage is negative. So for the positive advantage version, let's think of an example where our ratio exceeds our clipping ratio. And let's look at a ratio of 1.3. So say, for example, our ratio is 1.3. What we do inside this minimum function is we multiply it times the advantage. If our advantage is 1.0, then what we're going to be evaluating is our unclipped and clipped version. The clipped version is going to be 1.2 times 1, and the unclipped version is going to be 1.3 times 1. So we always want to choose the more conservative clipped one. Now, the reason we're showing this example is because it's a little bit more counterintuitive on the negative side here. So let's think about we have a dramatic ratio like 0.5, and we have an advantage of -1. What's going to happen here is our unclipped version is going to be 0.5 times our negative advantage, which is -1 here. And our clipped version, we're going to clip the ratio at 0.8. So it's going to be 0.8 times -1. We're always going to choose the minimum here. In this case, the minimum is our clip version of -0.8. So that's the more conservative estimate, more conservative update to the policy. So that's the gist of what PPO is really doing under the hood. But if you're anything like me, it's pretty hard to visualize what's actually happening until you can see it in code. So I sat down, I wrote my own version by hand based on OpenAI's original implementation, and I tried to keep it as explicit as possible. Just using a basic MLP, I didn't even use classes for the neural network, just pure scientific Python. And once you strip it down, it's really not that bad. There's not as much going on as you think there'd be. There are a few parts of the implementation that are worth explaining. The forward pass is one of these. So what we're doing here, if you look at the code here for the forward pass, what we're actually doing is we're feeding X, which is our observations, into the actor neural network, and we're getting our raw output. For our example, we have 3 actions. So we've got up, down, and do nothing. So it's just a raw number for each of those 3 actions. Now, what we have to do with that is we use categorical, which is giving us the probabilities for each action. This is built into Torch. So it's a Torch function that we're using here. It's basically like taking softmax to give us a probability of our 3 options here. Now, we have the if statement down here. So after we finish the rollout, we don't sample the actions again. So we allow the old actions to be passed through this function when we feed them in the learning phase. But during the rollout phase, we need those actions. So what we do is probs.sample here. This is basically like taking the probabilities that we got out of categorical and rolling a three-sided die that's weighted for those probabilities. And the reason for that, this is the part that's interesting that I think is worth explaining, is that's how we actually get randomness and entropy when we're training. Otherwise, if it's like a 0.7 for one action and then the other two add up to 0.3, it's always going to choose that action that's 0.7. What this is telling us is it doesn't always choose that action. It's just going to choose that action 70% of the time. And then down at the bottom here, you'll see that we calculate the log probability, the entropy, and then we also call the critic neural network with the observations. And you'll see, we'll touch on how we use that later on as well. This part is the GAE implementation. Rollout is done. We have all the actions, rewards, terminals, log probabilities, and critic values. Now PPO needs to answer the question, was that action better or worse than what the critic expected? Remember, that's what the advantage is. So the first thing we do is we call the critic one more time using next obs. This is called bootstrapping. Essentially, after the rollout ends after a fixed number of steps, the episode might still be going on. So we need the critic to estimate the value of the state right after the rollout ends. Then you can see in the loop here, GAE works backwards through the rollout. It starts at the final time step and moves all the way to the beginning. The reason for this, the reason it goes backwards, is because rewards happen after the actions. So if something good or bad happens, GAE lets that information flow backwards and assign credit or blame to the actions that preceded it. You can see here that at each time step, we calculate delta, which, as we remember, is the reward plus the value of the next state minus the value that the critic predicted for the current state. Then last GAE lam accumulates that surprise backwards through time. And once we have all the advantages, we add them back to the critic's value estimates to get the returns. That's what we use later in training. Okay, before we move on to the learning step, what we do is we flatten the rollout from a grid of num steps by num ENVs into one big batch of experience samples. This lets PPO shuffle that batch and pull out mini batches for training instead of treating the rollout as separate timelines. This section is the actual PPO learning loop. Rollout is done, GAE is done, and now we have the flattened batch of data that we're going to train on. At the start of each epoch, we shuffle the batch indices. This is randomizing the order of the training samples. But the important part to think about here is that we're only shuffling the indices. The observation, action, log probability, advantage, all of those are tied to each time step and stay together. Then we use those shuffled indices to split the full batch into a bunch of mini batches. In each mini batch, the first thing we do here is we call the actor and the critic again. But this time, we pass in the actions that we already took during rollout. So if you think back to when we talked about the forward pass, when we're passing in these actions here, that if loop is going to allow the actions to pass right through. The important part is that this gives us the new log probability. And from there, we can calculate the probability ratio. As we talked about earlier for PPO, that ratio is what we use for clipping. Something to take note of here is on the first epoch, we're calling this before we actually update the weights. So in this first epoch, the probability ratio is always going to be 1. But once we start updating the network, the weights are going to change and that ratio is going to start moving away from 1. Then we calculate the policy loss. If we think back to our equation for PPO, PG loss 1 is the normal advantage times the probability ratio term. PP loss 2 is the same idea, but this is the clip version. In the PPO paper, this is written as a minimum because the objective is being maximized. But in this code, we're using a negative sign in front of the advantage. You can see us passing the advantage in with that negative sign. And that's why we're using a PyTorch max function here. Finally, we train the critic. The critic loss is actually pretty simple. It's basically just mean squared error. The new value estimate from the critic minus the return target from GAE squared. Then below that, we apply the same general clipping idea to the value loss so that it doesn't move too much in one policy update either. Finally, we add the entropy term and we combine everything into the full loss. Zero the gradients, backpropagate with loss backwards, clip the gradients, and then call our optimizer step to finish this part of the process. Okay, before we talk about training, I need to very quickly explain how the super simple environment that I wrote works. So we have our agent, blue circle. We define our agent with a radius r. Then we have all of our obstacles, red circles. We define their size with a radius r. For every single one of these on our screen, we track them with an xy coordinate for the center and a radius for how large it is. Then in the update step, what we do is we take our agent and we apply the action that the policy chose. So in this case, it's discrete, it's up, down, or do nothing. Then we take all of the obstacles and we shift them left by 1 across the screen. The last part is our collision logic. So what we do is we take the center xy coordinates of our agent and we calculate the Euclidean distance to the center xy coordinate of all of our obstacles. And then we compare that distance to the sum of the two radii. So if the distance is greater than the sum of the two radii, then we don't have a collision, we continue. If the distance is less than the sum of the two radii, you die, game's over. So the first thing that really surprised me in doing this was how much hyperparameters actually matter. I started by trying to validate this simple environment in PufferLib, and even running, like 10 billion steps per second at first, I couldn't get it to learn. So after tuning some of the hyperparameters, basically trying stuff at random, I got it to start to learn, and then I started incorporating a hyperparameter sweep. And that's where I started seeing some interesting things. So for example, I would run a hyperparameter sweep and I'd get a result where the agent was finally making progress. Maybe the average episode went from -1 to around 0.2. So my instinct is like, okay, let's freeze these hyperparameters here and just run it for more steps. But that didn't always help. Sometimes doubling or tripling the number of steps gave me the same result, and sometimes even worse. I think this is because of learning rate annealing. So the way that I was thinking about it is when you change the total number of training steps, you're not just giving the agent more time, but you're also changing how long it spins at different learning rates. So something that worked for a shorter run doesn't always mean it's going to work for a longer run. I saw the same kind of thing with the number of environments. So in my head, I was thinking more environments, more data, more better. But when I increased the number of environments, I actually saw worse results in a lot of cases. And I think that's because if you keep the total number of steps constant, increasing the environments just packs more data into each update. But technically, you're updating the policy less times per experiment. This wasn't the case in PufferLib, as you can see by the plot that I'm showing here, but there was clearly a ceiling to how many environments were actually useful. So a lot of the difficulty here that I'm describing just comes from how I built my environment and the observations that I passed to the agent. So let's talk about what I did wrong. So in this code block here, you can see these are the observations that I'm feeding back to the agent. And essentially what I'm doing, those first 3 lines are pretty simple. We're basically just feeding back normalized X, Y, and radius positions to the agent. And then this loop down here is basically just collecting the same thing for all of our obstacles. But you'll see in the third to last and second to last line here that what I'm doing is I'm actually subtracting the agent position from the obstacle. And the reason I'm doing this is because eventually what I want to do is I want to use this for sonar data, which is essentially a measure of distance. So that's the only reason that I tried this in the first place. But this, I'll show you in a second, is a very inefficient way of giving the agent data. It's still learned, but I'll go through what I did at first, and then we'll compare this to a vision approach that I tried later. And there's a big difference. Okay, for all of my initial experiments, this is a representation of what I was actually feeding the agent. This is the bad approach here, where I'm feeding the XY distance values and the radius for all of the obstacles and the agent. This is what the run looked like once I finally got the bad version to actually learn. You can see that it took 4 billion steps for me to get there. So, and also pay attention to the wall clock time here. It took me about an hour and a half. Now, this is on the version of PPO that I wrote, and it's written for me to learn. So it's not optimized to be fast at all. An equivalent run, doing this equivalent run in PufferLib took me about like 10 to 12 minutes. So huge difference. Makes you really appreciate, what PufferLib can do. Now, when we overlay this plot with the same version, but me using pixels, it's pretty comical. For the pixels version, in this comparison, I'm using the exact same model size, exact same hyperparameters. The only difference is the data we're feeding in is now in the form of pixels, and I added a small convnet to the beginning. But you can see the wall clock time for the pixels version is about 10 minutes. But the sample efficiency, which you can't even see on the plot here, is just, it's so much better. I think we got to this point in about 2 million steps. I'll show the full plot below in a second. Here is the plot for that same run, but just for the pixels training. You can see that we get to a better result than the non-pixels version in only 2.5 million time steps. And the other thing that I should point out, in the non-pixels version, we needed that 512 hidden dim to actually get it to learn. Anything smaller than that, and I was having to run it upwards of 10 billion steps to get to the same stage. Another thing here is with pixels, I was able to make the model much smaller. So you can see here for 256 hidden dim, here for 128 hidden dim, and then here for a 64 hidden dim. Now, something I haven't figured out yet, which is pretty interesting to me, is why all of these drop at the end here. And I ran it for more time steps to see what would happen after this point. But again, I think it might have something to do with the loss rate annealing, which doesn't make any sense to me because the loss rate should be or the learning rate should be really small at the end of the runs here. So I don't know why it's having such a big effect on the policy for like the last 5%. This is a sped up version of both of the agents playing. The one on the left is the raw X, Y, and radius values version, and the one on the right is the one trained on pixels. It's pretty interesting to see how their behavior differs as you watch them go through it. The ultimate goal for me is to train an agent that can navigate purely off of sonar data. And the nice part is that sonar is really just distance measurements, so I think I'll be able to keep the environment really fast while staying pretty close to what a real sensor would actually see. To mock it, I think I can do something really similar to what this animation is showing here, where basically I'll assign a viewing window to the front of the agent. And then within that viewing window, I can add a bunch of evenly spaced vectors and measure the distance to whatever obstacles we have in our environment along each one of those vectors. And then once I have a matrix of distance measurements, I can essentially plot these from 0 to whatever I want my max distance to be. That can be turned into a 1D array where each index position represents a certain amount of time that we've waited since we sent out our ping. And then the values of each one of those index positions can represent the voltage spike that we see on the actual sonar. And then that can be scaled to be realistic for what we'll actually see, or we can normalize it to do whatever we need with the data. My goal is to get it as close as possible to what sonar data would actually look like, even if after the fact we're going to pre-process this in a way that might be turning it back into distance measurements. But I want to have a stable baseline that's fairly accurate. So next steps for me are I need to build a procedurally generated 3D environment with obstacles, then use mock sonar data as the agent's observation. From there, I can experiment with how I represent that data and move on to rigid body dynamics and eventually more accurate physics.